Control Charts Overview. Introduction. Control charts, your process's early warning system. Imagine driving your car without a speedometer. How would you know if you're going too fast or too slow? A control chart is like a speedometer for your process. It helps you see whether your process is running normally or if it's starting to go out of control. It doesn't just tell you the result, it shows you trends, shifts, and patterns over time so you can catch problems before they lead to defects or delays. It answers, is my process stable? Are changes happening naturally or because something went wrong? In short, a control chart is your process's early warning system, keeping you ahead of problems, not reacting after they happen. Agenda. Let's start with some practical examples to illustrate how control charts are used. In manufacturing, we might use an X-bar R chart to monitor part dimensions like diameter. In services, an IMR chart could track individual transaction or resolution times to maintain service quality. Moving into the introduction to control charts, these are essential tools in quality management that help monitor process behavior over time. They are especially useful for distinguishing normal variation from issues needing attention. Why do we use control charts? They help us maintain process stability, detect problems early, and drive consistent quality improvements. Their benefits include visual tracking, data-driven decision-making, and long-term performance control. There are different types of control charts. Attribute charts are for count data like defects. Variable charts handle measurable data like time or length. Choosing between them depends on the type of data and sample size. Key decision points involve when to use which chart. IMR for individual values, X-bar R for small subgroups, and X-bar S for larger ones. Every chart has key components. A center line, CL, that shows the process average, upper and lower control limits, UCL and LCL, for acceptable variation, and data points that reveal how your process behaves. When interpreting control charts, we apply rules to detect issues, like a point outside control limits, trends, or patterns that suggest instability or special causes of variation. In the control phase of Six Sigma, control charts are used to embed monitoring into daily operations. They help ensure improvements are not just one-time fixes, but sustainable over time. Finally, here's how to create a control chart. Follow a step-by-step process. Collect data, calculate limits, and plot results. While this can be done manually, tools like Minitab make it faster, more accurate, and easier to interpret. This gives you a full overview of how control charts can be practically applied to ensure quality and process stability in any environment. What are control charts? Control charts, also known as Shewhart or process behavior charts, are essential tools in statistical process control. They help us monitor whether a process is stable and operating consistently over time by checking if the data stays within control limits. This lets us quickly spot and address any unusual variation. Purpose of control charts. Control charts help determine if a process is stable by highlighting any unusual variations. They support timely corrective actions and are widely used to monitor business performance. Tools like Minitab enhance their effectiveness with advanced analysis features. Understanding specification limits. Specification limits define the acceptable range of a process or product. The lower spec limit, LSL, and upper spec limit, USL, are boundaries set based on different criteria. These can be customer-defined, self-imposed for internal standards, or regulatory as per industry laws. Anything outside these limits is considered out of spec, meaning it's a defect or failure. These limits help ensure consistent quality and performance. Understanding control limits. Control limits, lower control limit, LCL, and upper control limit, UCL, are calculated from actual process data, not set by the customer. They reflect the process's natural variation and show whether it's stable over time. Unlike specification limits, control limits help us detect when the process may be going out of control, enabling early corrective action before defects occur. Common cause and special cause variation. This chart illustrates the difference between common cause and special cause variation. Common cause variation is the natural fluctuation within control limits and reflects the stable, everyday performance of a process. But when a point falls outside the control limits, like the one near the UCL, it signals a special cause variation, indicating something unusual or unexpected has happened and requires investigation. This slide shows both types of variation. The left side represents common cause variation, which stays within control limits and reflects normal process behavior. The right side highlights a special cause as the point nears the lower control limit, LCL, suggesting an unusual event. Identifying and reacting to these signals is key to process control and improvement. This chart visually illustrates the difference between common cause and special cause variation in a process. The three bell-shaped curves represent distributions of sample measurements over time. The horizontal black lines mark the upper control limit, UCL, nominal, and lower control limit, LCL. The first two samples, sample 1 and sample 2, fall within the control limits. This type of variation is known as common cause variation, which is inherent to the process and expected over time. However, the third sample lies outside the control limits, which is an indication of special cause variation. This is unusual and likely caused by an assignable cause, such as a change in material, machine malfunction, or human error. The red dot outside the LCL signals a point that requires investigation, as it suggests that the process may no longer be in control. Understanding the difference between these variations is essential for quality control and continuous process improvement. Common causes are dealt with by improving the system, while special causes need immediate investigation and corrective action. This diagram illustrates the concept of process variation, specifically differentiating between common cause and special cause variation in quality control. Each of the three curves represents a distribution of process data over 3 sample periods. The horizontal lines labeled UCL, upper control limit, nominal, and LCL, lower control limit, define the expected range of variation within a stable process. For sample 1 and sample 2, the black dots fall well within the control limits. This type of fluctuation is known as common cause variation. It is inherent in the system and typically due to random routine factors. However, in sample 3, the red dot is located outside the LCL, indicating a special cause variation. This signals that something unusual has occurred in the process, perhaps a specific error, malfunction, or external influence. The note, "Assignable causes likely," emphasizes the need for further investigation to identify and eliminate the root cause of the deviation in sample 3. Understanding and distinguishing between these two types of variation is fundamental in statistical process control, SPC, and helps organizations maintain consistent quality and improve processes over time. Errors in control charts. This slide explains the two main types of errors that can occur when interpreting control charts, Type 1 and Type 2 errors. Type 1 error is also known as a false alarm. From a statistical standpoint, this happens when we incorrectly reject a true null hypothesis. In quality control, this means we mistakenly believe a process is out of control when in fact it's operating normally. This can lead to unnecessary adjustments, wasted time, and added costs. Type 2. Error is referred to as a misdetection. Statistically, it occurs when we fail to reject a false null hypothesis. In the context of quality control, this means we miss a real issue in the process, ignoring an assignable cause of variation. This can result in defective products and customer dissatisfaction. The illustration of the person overwhelmed by errors and alarms emphasizes the confusion and potential consequences of misinterpreting process control data, either overreacting to stable processes or underreacting to real problems. Accurate interpretation of control charts is essential to avoid these errors and maintain efficient, reliable operations. Patterns and trends. This slide explains how different patterns and trends in control charts can provide insight into process behavior, beyond just identifying points outside control limits. In control, when the data points show random variation around the center line and stay within control limits, the process is considered to be in statistical control. This is the ideal state, indicating that variation is due to common causes only and no intervention is needed. Clusters. Here, data points are tightly grouped together, indicating a temporary shift in the process. This pattern might not breach control limits, but can signal a potential issue. Possible causes include introduction of new staff, system issues, or seasonal factors like holidays, all of which can affect the process temporarily. Mixture. In this case, data points tend to avoid the center line and hover near the control limits, suggesting two or more distinct data populations. This could mean different processes are being lumped together or data is coming from diverse sources. Possible causes include parallel processes, mixed data types, like different customers or locations, or non-random sampling. Recognizing these patterns helps detect underlying issues even when all points lie within the control limits. It's a reminder that being within limits doesn't always mean the process is healthy. This slide continues exploring different patterns and trends in control charts, focusing on three more complex behaviors: unstable, stratified, and systematic variable patterns. Unstable pattern. This is marked by frequent and unpredictable shifts, where the chart may move out of control and then return. It signals an inconsistent process, potentially due to human factors or operational instability. Possible causes include reliance on manual work or operator skill, lack of standard operating procedures, inadequate training or high staff turnover. Such a process may need to be segmented or stabilized before any improvement can be effective. Stratified pattern. In this case, data points align consistently along the center line, with little spread toward the control limits. This suggests data from multiple subgroups that are not behaving uniformly, often due to combining results from different populations. Possible causes include multiple distinct processes or departments feeding into a single measurement, improper grouping of diverse data sources. It's often necessary to break the data into subgroups to get a clearer picture. Systematic variable pattern. This pattern shows predictable shifts, like a repeating low-high-low pattern. It reflects a cyclical behavior in the process. Potential causes: day-of-week effects, workload fluctuations, consistent scheduling patterns in tasks such as invoice processing. Recognizing these predictable trends helps in planning and adjusting resources or schedules accordingly. Understanding these patterns allows us to go beyond just detecting out-of-control points and start diagnosing underlying structural issues within the process.